All right, Ren. So today we're going to go over a couple of different exam PA topics, specifically on weights and offsets. This was a comment. This was a question on actually the last October exam PA that was pretty difficult, and I don't think many of the candidates got it correct. We'll go over sensitivity, recall, specificity, ROC, AUC curves, GLM assumptions, as well as some random forest decision tree parameters, how the trees are split. And then we'll move into some, I guess, Gini index, entropy, information gain, so more about random forest, and then also ridge and lasso as well, and also boosting as well. So we'll go into that. So first, if we go into weight, the difference between weights and offsets. So weights assign different levels of importance to the observations during model fitting. So this is something that occurs only during the model fitting process. You're assigning a different level of importance to the observation. So observations with larger weights will have a greater influence on the MLE coefficients. And again, this is only used in the model fitting process. So this is not used as like an explicit term in the model equation. So this is actually used when you have offsets, right? When you have offsets, they're explicitly used in the predictor, in the linear predictors themselves. So if you have, for example, like an exposure variable that you want to include that's already known about, let's say, for example, a region, and you want to include that variable, you can include it as an offset, as a fixed quantity that you want to add to the model as into the linear predictor. But you would use weights when you want to assign different levels of importance to the observations themselves. So if you want to give certain pieces of observations larger weights, you want to have them have a greater influence when during the model fitting process when it's estimating coefficients. Then you would use weights. If you already know like this is the fixed impact of this variable on the target and you want to include it without estimating a coefficient for it or without having it influence the rest of the coefficients, then you can just use offset as another sort of fixed quantity in your model. Then we look at sensitivity, recall, and true positive rate. So sensitivity, recall, out of the total number of actual positive classifications that we have, how many of those actual positive classifications did we correctly predict? So those are true positives over true positive plus false negative. Specificity is on the flip side, so the true negatives. So out of all of the negative classes, out of all of the negative actual observations, how many did the model correctly predict as negative? So that is also 1 minus the false positive rate. When we look at the ROC curve, it plots the true positive rate, so which we talked about the sensitivity or the recall, versus the false positive rate at different classification thresholds. So not just at 50%, but at 60, 70, at a range of classification thresholds, it's going to plot how the uh, FPR, the false positive rate, performs against the TPR. And then one of the differences between ROC and AUC is that AUC represents the area under the curve. So this represents how it's a scalar quantity. It's a single number that represents the ability of a model to distinguish between positive and negative classes, whereas ROC is more of a graphical representation of the performance of the model. And so those are the two main differences. There was also a question about this on October exam PA on what's the difference between ROC and AUC. And again, the model answer is that ROC is a graphical representation of the performance of the model by measuring the TPR versus the FPR, different classification thresholds. AUC is a single scalar quantity that summarizes the performance of the model, how it can distinguish between classifying between a positive and a negative case. An AUC of zero point 0.5 is akin to just random guessing. So if you have an AUC greater than zero point 0.5 or zero point 0.8, that means that the model has a moderate to strong ability to distinguish between positive and negative classes. GLM assumptions with another question on October exam PA, and we know the typical assumptions of linear regression, like the expected value of the errors, needs to be zero. You know, variance of the errors are constant; they're homoscedastic. But one of the assumptions of generalized linear models is that the target variable in linear regression it follows a normal distribution. But now in generalized linear models, the target variable follows a distribution that belongs to the linear exponential family. So in this case, it's referring to normal, Poisson, gamma, binomial distribution, uh, anything that belongs to that linear exponential family. We assume that the target variable has a distribution in that. And then another assumption is that, again, in the same case as linear regression, all of the observations are independent. And then also the relationship between the predictors and the mean of the response is linear. So that's also what we refer to as the link function that serves as a bridge between the linear predictor and the mean of the response. In the case of linear regression, our mean of the response is has a one-to-one relationship with the linear predictor. So the link is just the identity link, or it's just mu. Whereas if for Poisson, it's actually the natural log of mu, which equals the linear predictor. So you can see the canonical links of depending on the distribution of the target variable that you have on this table. And let's see, and then typically on the exam, when it asks for what sort of link function to actually use, you don't want to just give it, a this is the canonical link, so that's why we're just using it. You want to provide some sort of rationale behind like what the distribution you're using and why that specific link function. So in terms of like if it's matching certain ranges, so if it's a gamma distribution or if it's an inverse Gaussian, we're using it because you can't model not it can't model negative integers. It can only model non-negative integers. So that's a possible reason for using gamma or an inverse Gaussian. So you want to explain that as more of a reason rather than just saying that hey, canonical link is using logit or using log or using identity. That's why we're using it. You want to sort of convey what's the interpretability aspect of it, and you want to make that a reason and really push for that to be a reason rather than just saying, hey, it's canonical link. That's why we're using it. And then, okay, like as we mentioned before, ROC, graphical representation of classifiers performance across all the thresholds. And then AIC and BIC. So we know that AIC, BIC are both measures of how good the model fits, and it also penalizes for complexity. And we know that BIC actually has a larger penalty for the complexity of the model. So in general, it's going to have fewer predictors. It's going to favor models with fewer predictors than AIC does. We also have the principle of parsimony, which states that when you have models that are predicting in terms of accuracy around the same, you want to prefer a model that is more simple, that has fewer parameters, that is easier to interpret, and that is more generable. So that's the principle of parsimony. We want to have models that are explainable, that you can extract information from, that are easy to interpret as from a business case perspective, from a generalizability perspective, we want to have simple models, considering the fact that, hey, in terms of accuracy, they like a complex model or a simple model, they perform, relatively similar. And now, when we think about random forest as well, there's a couple of things to know here. So obviously, we have regression and classification. In regression, the way that the individual decision trees are constructed is you start off with, let's see, let's go to so you start off with the residual sum of squares at the root node, right? You calculate the residual sum of squares at the root node where you're comparing the actual predicted values, which would be the average, against the actual values. And then that will be your residual sum of squares at the root node with zero splits. Then you split, you consider possible splits depending on if you have continuous variables or categorical variables. For continuous variables, you typically consider the midpoints of the ranges of the continuous variable. For categorical, you consider the levels, and then you make the split for which there is the greatest reduction in SSE, right? So you test out all these splits, and then for whichever split you are able to attain the greatest reduction in SSE, you go ahead with the split. And then you continue doing this until you reach some sort of stopping criterion, which is four different stopping criterions that are mentioned here, which is the minimum number of observations to even attempt the split, the minimum number of observations in each terminal node after the split, the max depth of any node in the tree, and the minimum reduction in the SSE for a split to occur. So first, the minimum number of observations to even attempt a split. So if you're at a node and you see that this does not have enough observations to even attempt a split, that is a stopping criterion. You don't further split the node. Next, if you were to split the node and you get to a terminal node where it's lower than the minimum number of observations in the terminal node for after the split, then you don't split the node. Third is if you reach the max depth of any node in the tree. So if you were to split this node and you exceed the max depth, then you don't split it. And then min reduction to SSE, if you do split the node, but then you see that this doesn't achieve a reduction in SSE that is already given, then you don't split it. So these are the four sort of major stopping criterions for when you're splitting the decision trees. And then we also want to make sure that we're not overfitting, we're not growing, the decision tree as much as possible. We want to make sure we're again not overfitting, and to do that, we apply this sort of this complexity parameter, which essentially stops our tree from overgrowing. When we have a complexity parameter of 0, that's essentially the largest tree. We're not adding any penalty for complexity of or the number of splits or the number of terminal nodes. When we have a complexity parameter of 1, that is just the root node, like we are cutting out, removing all complexity. And we want to minimize this quantity here of the residual sum of squares, the error sum of squares of the tree, right? So of the subtree plus the complexity parameter times the number of terminal nodes. And again, the number of terminal nodes is always the number of splits plus 1 times the SSE of the tree with no splits. So you want to try to minimize that. So if you have two different trees, one tree with 5 splits, one tree with 4 splits, whichever tree has this lower quantity, it would prefer that tree. And you can see that in these tables here, where it suggests, or actually we even did an example over here, where what is the cost complexity value for favoring 0 splits over 1 split. And so we set up inequality, and we see that okay, if the complexity parameter is greater than or equal to 0.61, then it will prefer a 0 split tree, right? Or a tree with just one terminal node over any other node, over any other tree, right? And so after doing this, you can create a table in which if the complexity parameter is this, then this tree will be preferred and this tree will be pruned. So that's cost complexity. One of the ways that you can select the optimal CP value is through cross validation. So you select the one that has the lowest CV error. There's also the one standard error rule that you can use, which is the leftmost under the horizontal line, which contains the lowest CV value plus some standard error. Whatever the leftmost value is below the line, you can use that. Typically, you just use the lowest CV error as the for the CP value, or the CP value that has the lowest CV error. And then for classification, you're trying to maximize the information gain. So in terms of information gain, it's referring to Gini index or entropy, and we have the respective formulas for Gini index and entropy here. And then the only adjustment to the previous expression is instead of having residual sum of squares, you have classification error rate, and so you're going to be using that instead of the residual sum of squares or the error sum of squares. And then, so again, how Gini index works is you calculate the Gini index at the first node, at the root node, and then you perform a split and you calculate the Gini index at the child node, the left child node, and the right child node. Take the weighted average of those by the number of observations that are in each node, and then you see what is the maximum number, what is the greatest information gain that you get from a single split, and then you proceed with that split. So this is what we refer to as recursive binary splitting, where you actually only look at the best immediate step. So that's why it's a greedy algorithm. Again, similar to how we did the recursive binary splitting in the regression trees. And then also, typically, we want to have a balanced tree as well, balanced decision tree. So sometimes when you have a very dominant variable that's, very right skewed, the tree might just split that variable on and on. So this leads to a very unbalanced tree. Uh, and so to avoid that, to fix that, you can transform the right skewed variable using natural log, and that will create a more balanced tree. One of the disadvantages of decision trees is that they are very prone to overfitting, especially if you don't provide a stopping criterion for the number of terminal nodes, or if you just let the tree grow as long as um, let the tree grow like for a very long period of time, then it's very prone to overfitting. Now, one of the ways to combat that is by using random forest, which is an ensemble of decision tree where each tree is trained on a bootstrap sample. So if you have, let's say, 1,000 data points, you sample with replacement, let's say, depending on the number of trees that you have, and that's hyperparameter, each tree will be trained on that bootstrap sample. So if you have 1,000 data points, the tree will be trained on a bootstrap sample of those 1,000 data points. So they won't they it's probably likely that they won't be unique. There will be some duplicates because you are sampling with replacement. But let's say, for example, you have 10 different trees, right, tree 1 to tree 10. Each of those specific trees will be trained on a separate bootstrap sample, and that bootstrap sample comes from the original training data set. That comes from the original training data set. So if your original training data set has 1,000 data points, your bootstrap sample for each of those decision trees will also be 1,000, but they won't necessarily be the exact same 1,000 because you're random sampling with replacement. And one of the things that this does is this ensures that each tree is being seen to a different part of the data set, right? Every tree is being trained on a slightly different version of the original data set, and this actually reduces overfitting once you average all of the predictions from the individual trees. In the case of regression, in the case of classification, is if you consider the majority vote. Some hyperparameters in decision trees, min number of observations in the nodes. We already went through this, but the hyperparameters in the random forest is the number of trees. Now, increasing the number of trees doesn't actually cause overfitting because of the fact that we're averaging across all of the trees, and so this essentially smooths out the model, and then it improves generalization as well because we're using a combination of trees, and this reduces overfitting. There's also the mtry hyperparameter. So this is the number of features considered at each split. Now you don't want to consider all features at every single split. One of the reasons is because if you have a very strong predictor, all of those trees are going to have sort of that strong predictor in a majority of those splits, which may cause correlated predictions coming out of the decision trees, which would increase your overfitting. So you want to make sure that each decision tree is contributing some sort of unique information to the prediction. And the way that you do that is by ensuring that the features that are considered at each split are random. So if you randomize the number of features considered at each split, the every single decision tree will have a slightly different feature set that it's using to construct the tree, which will mean that its contribution to the overall prediction will be unique. And so that's ultimately what we want to reduce overfitting. And a couple of other terms. So bagging. So there's two like terminologies related to bagging. So the first type of bagging is when we're aggregating the bootstrap samples from the decision trees. And then we're doing this majority vote in the case of classification or averaging the predictors in the case of progression. So that is bagging. Another terminology is bagging, but in the sense where all the features are considered for every single split. So as we discussed previously, that's one of the hyperparameters that we can tune. But if we just have it so that all the features are considered at every split, that is considered bagging, just a terminology. Another thing is boosting. So boosting is another methodology where trees actually grow sequentially from the information from a previous tree. So you use the previous tree, you start off with a baseline model, a simple tree, you make your predictions, then the next tree actually tries to improve upon the errors that the previous tree has made through the shrinkage parameter, through correcting the errors. And so one of the parameters that we have is number of trees. Also, this is common with the uh, bagging approach and just with general random forest. We have the number of splits, we have the shrinkage parameter, so this determines how much the model changes after each new tree is added. So this is sort of you can think of this as the learning rate. What is the influence of each tree on the overall prediction? And if you have you want to have like a slow, gradual learning rate, just so the model doesn't overfit. We talked about AIC, BIC. Typically, forward with BIC means that you have fewer predictors, which are easier to interpret. Backward with AIC means you have a more flexible model. Hierarchical principle refers to the fact that you only add interaction terms if the individual terms are already included within the model. So if you have, let's say, x1 and x2, you only include the interaction between x1 and x2 if x1 and x2 individually are already included in the model. Lasso and ridge regression are both regularization techniques to prevent overfitting, right? To increase underfitting to increase the amount of generalizability you have in your model. We know that lasso is a feature selection technique, so the coefficients could equal zero. And we know that ridge, the coefficients could approach zero, but they can't actually equal zero. So lasso is a feature selection technique, which means that it's more interpretable as well. But they both work for high dimensional data. So again, some of the common questions I've seen are the hyperparameters on the random forest. Um, Specifically, why does increasing the number of trees not increase overfitting, right? Generalized linear models, the assumptions of generalized linear models, selecting the link function and the distribution of the target variable, doing sensitivity, specificity, and accuracy, calculating those, the difference between weights and offsets, difference between ROC and AUC, the different performance metrics. So those are a couple of the other things. Also may be asked to possibly, uh, look at a random forest, go through it and provide a prediction for a particular observation, or even select an optimal complexity parameter value as well. So these are some concepts in PA. I'll see you in the next video.